It is my great pleasure and honor to introduce our last keynote speaker, Kunle Olukotun. He is the Cadence Design Professor of Electrical Engineering and Computer Science at Stanford University. He's also the Chief Scientist, Technologist, and co-founder of Samba Nova Systems, developing advanced systems for machine learning based on reconfigurable AI processors. Kunle is well known as a pioneer in multi-core processor design. He founded the Faro Web Systems to develop high-throughput, low-power multi-core processors for server systems, and some of that work is now powering all Oracle Spark-based servers. He currently directs the Stanford Pervasive Parallelism Lab, and he is also a member of the Data Analytics for What's Next, or DAWN Lab, which is developing infrastructure for usable machine learning. Finally, he's an ACM Fellow, an IEEE Fellow for contributions to multiprocessors on chip and multi-threaded processor design, and he's a recipient of the 2018 IEEE Harry H. Good Memorial Award. And so it is with great pleasure that I introduce to you Kunle.
Good afternoon. So it's a pleasure to be here, and thank you, Hugo, for that kind introduction, and thank you to the organizing committee of NeurIPS for inviting me. This is a huge conference, and I'm glad and honored to be here. So I'm a computer system designer. I've done computer systems design for many years, and it's a particularly interesting time in the kind of evolution of computer systems design, and that's because it's characterized by two important trends. The first of which you're quite aware of, that's the broad success of machine learning, and this conference is an example or representative of how much interest there is in the machine learning space. When I first came to this conference about 12 years ago, it was much, much smaller. And so the fact that the interest in machine learning is being driven by the incredible advances in image recognition and language understanding and knowledge-based creation. And these sorts of innovations and advances are having societal scale impact, right? So they're enabling autonomous vehicles, greater new scientific discovery, and all sorts of innovation in the medical and personal medicine sphere. So the interesting thing from a computing point of view is that building these ever more interesting, complex machine learning models takes a huge amount of computation. So you often want to train on terabyte-sized data sets. You often want to, if you're a large web company, you want to serve millions of your users using these machine learning models. And so there's huge amounts of, or almost insatiable, demand for computation. So that's the trend that you're all familiar with. The other trend, which you might not be as familiar with, is the fact that Moore's law, which has kind of driven the computer industry for the last 50 years, is basically slowing down, right? So Moore's law, of course, says that every 18 months or 2 years, we double the number of transistors on a chip, which means, of course, the systems that you can build with these chips become cheaper and more capable. But what's happening is, of course, we're stretching out beyond every 2 years per circuit generation, and we can argue how much stretching is going on, but what's clear is the companion law to Moore's law, which is known as Dennard scaling, is absolutely dead. Right? So Dennard scaling says, if I double the number of transistors on a chip, I can basically use the same amount of power. And so if Dennard scaling is dead, if I double the number of transistors on a chip, then I double the power. And that basically means that all computing is power limited. And what that means is that the conventional way of designing computers using CPUs basically is stagnating. You can't get more performance because anything that you want to do is basically power inefficient. Okay, so that's the backdrop. The interesting thing, of course, then, is that given the huge demands from machine learning for performance and the fact that the traditional ways of providing that performance have run out of steam, what we need then is a new approach to designing computer systems for machine learning. So the intermingling of machine learning and more computer power actually is has been going on for quite some time. As you all know, neural nets has been around for a long time, 50 plus years, and training them using backprop has been around since the 1980s. And so the question is, why did they become so dominant? And clearly, this graph kind of gives you a sense of what went on. On the x-axis, we have the data set size and the model complexity, which of course has grown over time. And on the y-axis, you have the accuracy on some task, be it, say, image recognition or language translation. And so in the 1980s, the data sets were so small and the models were so simple that they couldn't beat conventional algorithms. But fast forward to today, and you've got 1 million times more computation, much bigger models, much more data, and now, of course, the neural network approaches are surpassing conventional algorithms by a large margin, and on some of these tasks that humans do, they're approaching or surpassing human accuracy. And so this notion of training, of developing software by doing neural net training has been characterized by Andrej Karpathy of Uber, or formerly a Stanford PhD student, as software 2.0. Right? So software 2.0, when I first heard the term, I said, this is pretty pretentious. You're going to change completely the way that we develop software, but it's grown on me, and the whole idea nicely captures the idea of, instead of developing algorithms in the traditional way, you train neural net weights based on optimization. And this approach to developing software, software 2.0, has a lot of fundamental advantages, right? So first of all, of course, it's often easier to develop to train a model than it is to actually manually develop algorithms. But I think more than the development of the model, one of the big benefits of deploying these neural network models is they are much more predictable in terms of runtime and memory usage compared to conventional algorithms. And this has a lot of benefits from a deployment point of view because, of course, you want things to be predictable. An example, of course, is Google's language translation, and they shrank their implementation from 500,000 lines of code to just 500. However, it's not just these high-end applications of sort of language translation and image recognition that can benefit from the software 2.0 approach. Even classical problems in computer systems, such as networking and databases and compilers, can benefit from the software 2.0 approach. And people who are taking this approach are radically changing what they're doing, right? So instead of developing algorithms, they are spending a lot of their time dealing with training data, and this means that they are fundamentally changing how they spend their time. So this idea of kind of creating and engineering training data is the new challenge then for developing software 2.0 applications. And there are a number of things, of course, that you do when developing training sets. You might come up with noisy labeling schemes using weak supervision. You might spend a lot of your time doing data augmentation to generalize your models, and you might do data reshaping. So Snorkel is a research prototype that's being developed at Stanford by Alex Ratner, who's on the job market academically, by the way, and his advisor, Chris Ray. And so Snorkel provides a way of accelerating and characterizing and formalizing these workflows that you use in data programming, and it makes it possible to combine these workflows, and these workflows are often noisy, and so typically you need to denoise the workflows in order to generate high-quality training data that can be used to generate high-quality models. So what are the implications of the Snorkel approach? Well, one of the implications is the intermingling of what was data data analysis and machine learning, right? So in this example, in this case, you're doing some weak supervision, and so rather than simply loading files sequentially from someplace in memory, you're actually doing an SQL query, right, in the middle of your machine learning training loop. And so this is fundamentally adding data processing to machine learning, which is a change from what typically was done before. The other thing, of course, that you're seeing is the use of sparsity in machine learning models, right? And so sparsity is becoming a design objective, right? So for instance, in some large neural networks in the fully connected layer, the number of parameters grows quadratically with the number of neurons, right? And so recently there's been some work that shows that, hey, if you use sparsity, you can make that growth be linear rather than quadratic, and this, of course, will dramatically improve the time it takes to train the model. Another example where sparsity comes up is when you're trying to model the real world, people's, places, things, and you're trying to use this to improve your training of your models, and so you end up with a fundamentally sparse network structure, and so sparsity again shows up in the modeling of your networks. The other, of course, big trend in machine learning is, of course, is greater complexity for the models. So the models are growing in complexity because, of course, by having more complex models, you can get higher accuracy. So this just shows that, from over the period of 2 years, the growth of the model size from 60 million parameters to 8.7 million parameters, and this is commensurate with a order of magnitude increase in the amount of computation required to train the model. So fundamentally then, machine learning training is limited by computation. So there's a quote from Greg Diamas, who was, or at the time he made the quote, a senior researcher at Baidu, and he basically says that the job of training machine learning models is limited by compute, and basically if we had more compute, we would train more complex models and get higher accuracy, and what we'd like is a 100x improvement in the performance of our computers so that we could train more interesting models. Okay, so that's the story for machine learning from a computation point of view. Well, what about the story of computation? Well, so this is a graph that kind of shows you the trends of microprocessors over the last 45 years. And what we see is a number of curves. The top curve, which is the golden triangles, show the transistor growth. So this transistor growth basically follows Moore's law. And then the red triangles, thank you, show the power that is dissipated. And so basically, on a chip, if you dissipate more than a few hundred watts, and you don't have very exotic cooling, then typically your chip will melt. And so you're limited to a few hundred watts of dissipation. And so that cap with the end of Dennard scaling means that the frequency, as shown by the green squares, has basically plateaued. And that means that your single core performance plateaus. And the only way to get more performance going forward is, what the industry did was turn to multi-core, right? So Moore's law, power wall, so this plateauing in the amount of power is known as the power wall. And back in the mid-90s, my research group did a lot of work on figuring out how to do multi-core. It didn't actually take off in the industry until mid-2000s, but that was basically the last time that we changed the paradigm in which we design microprocessors fundamentally. But notice the software really didn't change, right? So it might have become more parallel, but we were still basically using instructions as our mode of executing programs. Okay, so let me say a little bit about power. And so power, as we said, there's a very simple equation which relates power to performance. And so power is equal to operations per second times joule per operation. Now, we said that the amount of power you can dissipate is fixed. And so, of course, you want more performance because we just said machine learning needs a lot more performance. And so then the only way to make this equation stay balanced, of course, is to become more energy efficient. We have to decrease the amount of power dissipated per operation. And so the way to do that is potentially to become more specialized, right? So if you do something in a fixed functioned way, you make it less flexible, less dynamic, less general, then you can make it more efficient. And so better energy efficiency basically comes from specialization or fixed function. So given the setup now, what are the key questions we want to address? Well, first of all, we certainly want to understand how we can get 100x improvement in performance so that you machine learning researchers can do more interesting things. However, as I said, the only way to do that is to become more power efficient. So we have to become more power efficient. So we need improvement in performance per watt. And we want to do this without giving up the flexibility that you traditionally have been accustomed to, right? So we don't want to do this by fixing what you do, because then you won't get to innovate, right? And so we want to be able to essentially give you fixed function-like performance with processor-like flexibility. That's the hard question that we want to address. Okay? And I would contend that in order to answer these questions, we need a full vertically integrated solution that combines new machine learning algorithms, new languages and compilers, and new hardware, all designed or co-designed together. All right, so let me say a few words about ML algorithms, and basically the outline of the talk will follow the 3 points I just mentioned. So ML algorithms, right? So the insight here is that machine learning is this brand new type of computation that follows a different model from the Software 1.0 model. Software 1.0 model, the computation had to be deterministic and repeatable because humans were programming with algorithms, and of course they want to get the same answer every time they run the program with the same input, and they want to be able to debug their program, so things have to be predictable and deterministic. Software 2.0, what you're really trying to do, of course, is learn these probabilistic models trained on data, and you only have to be as accurate, or you only have to be statistically correct in order to get the requisite accuracy in your models. And so by taking advantage of this, creates lots of opportunities for improved performance, right? So machine learning basically is an computer architect's dream, right? It's this world in which fundamentally you need lots of computation, but there's all sorts of ways of getting to the right answer, right? And so that creates lots of opportunity for innovation, and you're seeing that. If I transported you to a computer architecture conference, there'd be many, many sessions on how to improve performance for machine learning, because it's something that, of course, has captured a lot of people's imaginations for the reasons I just described. Okay, so the core algorithm in machine learning training, of course, is stochastic gradient descent. Now, you might use other techniques, but this is one is basically the most dominant one. And of course, the key idea is to take some element of the training set, compute the gradient, and move in the opposite direction. All right, so one way of characterizing SGD is in terms of efficiency. There are 2 types of efficiency. Statistical efficiency, which is how many iterations it takes for you to converge to a particular level of accuracy for your model. And then hardware efficiency, which is how long each of these iterations take. Now, clearly, in order to understand how long the whole SGD algorithm is going to take, you've got to take the product of these 2 efficiencies. However, from a system optimization point of view, what you'd like to do is to trade off some reduction in statistical efficiency for maybe a much larger improvement in hardware efficiency. So, one of the places where there is some debate within the machine learning community is on batch size. So this is a fundamental trade-off between hardware efficiency and statistical efficiency, and you can decide sort of where you want to be. But let me talk about another kind of trade-off, and that is lower precision, right? So low precision is an area where you can make this trade-off, and fundamentally, if you compute with integers instead of floating point numbers, or you compute with 4-bit integers instead of 64-bit integers, you will save a lot of energy. So quadratic in the size of your integers, and they're multiples of power saved if you go from floating point to fixed point. Also, of course, the sizes of your data set size, both the activations and the weights, are going to get smaller if you use lower precision. And this means, of course, you're going to use less memory capacity, but also when transferring that data, you're going to use less memory bandwidth when you do that. And so it has memory advantages. Also, of course, it has computational throughput advantages because you can use specialized instructions that operate on multiple data elements at the same time. These instructions are called SIMD instructions, or SIMD instructions, and many many processors take advantage of that. So examples of where lower precision has been used in the Google TPU. Intel has specialized SIMD instructions for exploiting smaller data types than 32-bit floating point numbers. And of course, if you look at the Microsoft Brainwave project, which uses a technology called field programmable gate arrays, which sometimes people call programmable gates or programmable hardware, then again, the only way that works well is by using low precision. So what's the downside to lower precision? Well, you've got lower accuracy, and that means that potentially you might hurt your statistical efficiency. And the sort of conventional wisdom is that you need at least 16 bits of floating point numbers with 32-bit accumulate to actually train using lower precision. Recently, we've come up with an algorithm that does somewhat better. It's called high accuracy, low precision. And the key idea is to use a technique called bit centering. And basically what you're doing is you're dynamically moving some fixed number of bits around so that you get the least amount of error. And so the idea is to bound the solution of your space and then move the bits to cover that space. And that's the recentering and rescaling component of the algorithm. There's also a statistical variance reduction component of the algorithm. And so if you compare HALP, which is shown in orange or pink, with the 64-bit variant reduction algorithm, SVRG, you see that it comes pretty close to the test accuracy of the 64-bit SVRG algorithm using 10 bits of HALP. And it turns out, of course, if you are using a model that is convex, you can prove that HALP will converge at a linear rate. But of course, most interesting models are not convex, and so you don't have the same sort of guarantees. However, you do see in practice that HALP works pretty well. This is just an example from a 14-layer ResNet on the CFAR 10 data set. It shows that HALP, shown in orange, gets you lower training loss and higher validation accuracy compared to stochastic gradient descent with 32-bit floating point numbers. And so lower precision is a good thing, but there are other ways of trading off better hardware efficiency for better hardware efficiency for some small reduction in statistical efficiency. The general sense or idea that I when I talk to my computer architecture friends is I say, just relax. It's only machine learning, and there's all sorts of things you can do. You can relax precision, as I just showed you. You can relax synchronization. If you write a parallel program, you can ignore the races and get rid of synchronization and ignore the races. which is something which is anathema to any parallel programmer, right? I teach parallel programming, and if I tell students, rule number 1, if you touch shared data, put in synchronization. Well, you can get rid of synchronization, and things will still work correctly. Now, if you look at a shared memory multiprocessor on chip or multiple chips, one of the key pieces of technology is called the cache coherence algorithm, right? It keeps all the caches coherent or consistent. And this is a really gnarly piece of logic. It's hard to design and make perform correctly. It's hard to get right. And it always is a rich source of bugs. Well, we found out that for machine learning algorithms, at least SGD, you don't really need it. You don't really need it most of the time. Like you can throw it away 99% of the time, and you still get the right answer. So you can relax cache coherence. In a distributed environment, you can reduce the amount of communication you do by analyzing the gradients and only transferring the gradients when they're big enough. Of course, if you do this naively, your statistical efficiency will go into the toilet. However, if you compensate by playing with the momentum, you can still make things work correctly, and you can get rid of a lot of communication by doing this. Okay, so all of these tricks fall under this idea of sort of how can we get much better hardware efficiency for some small reduction or maybe even no reduction in statistical efficiency. Okay, and here are 3 recent Stanford PhD students who've kind of done a lot of work in this area. Okay, so now we've got new algorithms. We've got algorithms that are optimized for modern hardware, and now we'd like to make those algorithms actually run fast on modern hardware. And we want to do so without having to understand all the details about what happens underneath with modern hardware. And so this is the realm of domain-specific languages and sophisticated compilers. So everybody is aware of domain-specific languages, right? So the idea is that I want to do a particular task, and if I can write in a language that has operators and data types which are just well matched or tuned to that task, then I can be a lot more productive. Okay, so a big example, of course, of that in the area of matrix and linear algebra is MATLAB, which you've all used, and there are others like SQL in the area of database processing. So these languages are usually high level and declarative. They say what you should do rather than how to do it. And traditionally they have been focused on raising the productivity of the application developer. A few years ago, we decided that, hey, one of the other benefits that you could get from domain-specific languages is as a driver for high-performance implementations, especially in heterogeneous computing environments composed of GPUs, CPUs, clusters, and the like, right? So you'd like to program once and optimize on multiple different platforms. So we came up with a language that we called Optimal for machine learning. Some say, look at it and say OptiML, but it's actually Optimal. And the idea is that this language was embedded in a general-purpose programming language called Scala, right? So this is just an example of k-means clustering. So it's a few lines. You calculate the distances to current means. You assign. You come up with clusters, and then you come up with the means. With new means by finding the centroids of the clusters. And so the point is that it's just a few lines of code. There's no explicit parallelism. There's no distributed data structures as you would see in an environment like Spark. There's nothing that says this is how you run on a GPU, this is how you run on a cluster, but yet from this description we can get very high performance implementations on all of these platforms. So fundamentally, of course, what we're going to get from this domain-specific language is a graph, but we're going to create this graph implicitly, right? As opposed to TensorFlow, which fundamentally is the same sort of idea. It's a domain-specific language for machine learning, but here you're doing explicit graph construction. So what we see for the same sort of algorithm is some slightly more longer description, which looks somewhat more cryptic. Now, there's nothing to stop you from kind of applying the approach that we took in optimal to TensorFlow, and in fact, I think one of my collaborators is looking at doing that. And so it is possible to do better than TensorFlow by using some of the techniques that we use in optimal. If you're interested in them, I'd be glad to talk to you about them afterwards. Okay, so what you'd like then is, you'd like your machine learning application composed of a bunch of DSLs, and as I said, in environments like Snorkel, you would need to combine some SQL processing with machine learning processing. And what that would mean is that you would have an application that had multiple DSLs. And then the question is, how do you optimize your application together? Well, that requires that you convert all of the DSLs into a common intermediate representation. So that's what we did. And we came up with a common intermediate representation based on what we call parallel patterns, or what people call parallel patterns, right? So these are basically functional data parallel transformations on collections. The collections could be sets, arrays, tables, n-dimensional matrices. And here are some patterns listed here: map, which you're familiar with, zip, reduce, flat map, and group by. And so here is the representation of k-means using our parallel pattern representation. And so one thing to notice is, of course, it's more lines of code because this is a lower level of abstraction. The other thing to notice is that the patterns, which are shown in blue, are actually nested. So a flat representation like MapReduce won't do the trick. You need nesting in order to capture the, to be expressive enough to capture what you want for machine learning applications. Okay, so once you've got a representation like parallel patterns, you can do a number of optimizations. You can optimize locality. Those of you who know about parallelism know that figuring out how to use local memory efficiently is key to performance, right? So you need to be able to do that, and you need to be able to do that automatically. And of course, this is an area of work that compiler people have worked on for a long time by looking at loop nests and optimizing them. Turns out that the techniques that have been pioneered, traditionally been pioneered in the compiler community, don't really work on parallel patterns. Turns out that parallel patterns are a little more complex. They're not what we call affine loops. They've got flow control in there, you know. So turns out that you need different techniques, but you can make things work and do the sort of optimization you need for local memory. The techniques are called tiling and, of course, fusion. And fusion is this really powerful technique that can get rid of a lot of intermediate memory. The other thing you want to do is create as much parallelism as possible because, you know, you might need it, right? You might have some accelerator or some hardware that can use all this parallelism. So you want to be able to generate a lot of parallelism. And you might want to be able to generate this parallelism in instances where the components of your program have dependencies. And the way to do this is using a technique called pipelining. So pipelining is a really important technique. And so pipelining is a technique that we've used. And basically, we show that using pipelining, we can, using these techniques, we can get dramatic improvements in performance. This is one example. This is working with a colleague of mine, Vijay Pandey. And he was looking at folding, protein folding, and using a technique called Markov state models. Originally, they wrote it in Python. It was way too slow, so they got a CS undergrad to take that Python code and convert it to C++, and then x86 assembly language, and it sped up by 1,500 times. Then that student left for Google, and they didn't know what to do with the code, right? And so what we did is we came along, we took the original Python code, converted it to optimal, and then we were able to get the same performance on a Intel processor as the hand-coded result, and then we were able to take that same optimal code and run it and generate a GPU code and get another 2.5 times performance improvement. Okay, so we have sophisticated compilation. approach that can generate code for instruction set processes. What about hardware acceleration? So today, the current approaches are CPU, which uses thread and specialized SIMD instructions, GPUs, which uses a massive number of threads, specialized SIMD instructions, and of course, specialized memories. And an example of a TPU, which uses a big multiply unit, matrix multiply unit, and a software managed cache. And the question is, what's next, right? So what do we need to do to get 10 to 100x improvement over these accelerators? Well, you could do something very specialized, but the problem is there are a lot of ideas, right? So this graph from Jeff Dean shows that the number of machine learning papers on arXiv is outpacing Moore's law, so more than doubling every 2 years. And somewhere in there, probably there are lots of good ideas, but you don't know exactly which ones. And so figuring out how to translate those ideas into a hardware implementation will take you 2 years. And by that time, there'll be 1,000 new ideas, right? So this is not really an approach of translating papers directly into hardware. And so if you kind of look into your crystal ball about the future of machine learning algorithms, it may be clear or it might be cloudy, but it's not you're not going to know exactly what's going to come down the pike. But we know that there are a number of things that look interesting. First of all, this whole idea of hierarchical parallel patterns seems to be very central. We can express all of machine learning and all of data analytics using these parallel patterns. Dynamic precision seems to be an important idea for supporting algorithms like HALP. Sparsity is going to be very important because, of course, we're going to want to reduce the amount of computation we do. And then, as I said, data processing in the inner loop of ML training means that that will also be important. The other thing to note is that I think the current interface to hardware accelerators is too narrow and too restrictive, right? Traditionally, you think of parallel programming models, some interface, or so some programming model, some interface, and then hardware. So traditional interfaces, of course, an instruction set architecture like x86 or ARM. So you could start with C++, go through an instruction set architecture, and that would be implemented by CPU. If we're using GPUs, you could start with CUDA, go through PTX, and end up on a GPU. The problem with the instruction set architectures are that you have a fixed set of operations, and they're usually defined at the low level, and so if you want more interesting things, you've got to combine them together. And fundamentally, executing instructions is inefficient. It's got all kinds of overhead. And we said efficiency is really the key going forward because we're really power limited, so we want to make things as efficient as possible. And so the approach that we would advocate is something which is much closer to this fundamental programming model that I said underlies all of machine learning and data analytics, this idea of hierarchical parallel patterns. And the interface is what we're going to call hierarchical coarse-grained data flow. And the idea is that it's much closer to the algorithms and allows you a much wider interface between the programming model and the hardware. So we have a representation of this interface, and we're calling it spatial, and it's an open source language. It represents the parallel patterns as a hierarchy of pipeline data paths, and it has an explicit memory hierarchy, so you can control with software how the memory gets moved between the different memories in your accelerator, or your hardware accelerator. Just to show you a really quick example of spatial, suppose we wanted to do dot product. Of course, the core of every machine learning algorithm is dot product, right? And so here's dot product with using parallel patterns. It's just a zip and a reduce. If you tile it, then of course you're going to get a two-level representation where you have a reduce, and inside the reduce is a map and a reduce. If you look at the spatial code, what will happen is you're going to declare two vectors in DRAM, and you declare 2 tiles in SRAM, and then you're going to move a piece or a block of the DRAM into one of the tiles, tile A, and then a block of the second vector, vector B, into tile B, and then you're going to do a reduction within the tile, and then you're going to do, in the outer reduce, a reduction across the tiles. Okay, so this 2-level reduce. Turns out that the hardware you get looks somewhat like this, right? And if you convert that into hardware, then you've got lots of design parameters that you can play with. The sizes of the buffers, the amount of banking in the buffers, the amount of parallelism and pipelining you do in the outer reduce, the amount of things you fetch at the same time from the DRAM into the SRAM, the amount of parallelism you exploit when doing the inner reduce, and what you want is an environment that can explore the design space and come up with something that's optimal for the particular hardware target that you are after. So now if you're looking at the compiler architecture, as I said, you start with high-level DSLs. You use a common intermediate representation that can allow you to optimize across the boundaries of these DSLs. You optimize the locality and parallelism using parallel patterns. You generate spatial, which is this wide interface to hardware accelerators. And then, of course, you need to map it to an accelerator. So here's an example. It's one called plasticine. So we're in Canada. So Canadians know what plasticine is. I grew up in London, so I know what plasticine is. Americans don't. But it's not like Play-Doh. The key thing that's different about it is it never hardens, right? So it's always pliable. So that's plasticine. So so plasticine then is a architecture that implements parallel patterns. Its key components are a configurable compute unit called a pattern compute unit and a configurable memory unit called a pattern memory unit. And you put these things together, and then you can create whatever hardware you want for the particular machine learning algorithm that's of interest by going through spatial, right? So here's a way in which you get to design hardware without actually going through the process of fabrication. And the question is, of course, how much overhead did I give you in providing this performance? Okay, so in order for you to map to this hardware, of course, we need a way of going from some spatial representation, which I just showed you the example for dot product, into something that can actually program this array of pattern compute units and pattern memory units. And so, here's a very simple example. I've got some address generation hardware. I'm going to map my the stuff that moves data from DRAM to SRAM in that. I'm going to map my compute to one of the pattern compute units, and it's going to not fit in one, so I'm going to have to go to another. I'm going to connect all the pieces together, and then the performance I'm going to get is going to be better than a GPU or a CPU, because we're going to more directly implement the algorithm. And the question is how close we get to an ASIC. So this graph shows energy efficiency in terms of megaops per milliwatt versus reprogramming time, which is some measure of flexibility. And what we see is that GPUs and CPUs are basically 3 orders of magnitude worse than a fixed function ASIC. And the goal of the software-defined hardware, an example being plasticine, is to get within a factor of 5 to 10 of the ASIC while being much more flexible, while being only a little less flexible than a GPU. So let me conclude by saying, this is a very interesting time in the evolution of computer systems. And it is possible, given that the end of Moore's law and the great demands in computer performance required by machine learning, and it's time in which we can, in fact, have it all with Software 2.0. And having it all means having all the Ps, right? Having productivity, power, performance, power efficiency, performance, programmability, and portability. So productivity we'll get by you having people develop applications using by doing training rather than conventional algorithms. And these training will be done by using new machine learning algorithms that trade off reduced statistical efficiency for much greater hardware efficiency. These algorithms will be implemented using high-performance domain-specific languages, and these languages with sophisticated compilers will be used to generate intermediate representations that can drive optimized implementations of hardware. And I hope that in the description of a vertically integrated stack for software 2.0, you are convinced that in order to actually have it all, you do need the vertical integration. And at this point, I'll end and ask if there are any questions.
So that was awesome. I happened to have dinner with Bill Dolly, one of your colleagues at Stanford, and I asked him how many hardware companies, startups are out there, and he said that he's lost count at 50.
Right.
And here's the question. The question is, can you give an estimate for how much investment is being made into this sector of hardware? I mean, overall, I know Intel, all the big companies are also making investments, and what's the scale here?
Oh, billions of dollars.
Billions?
At least $1 billion, yeah. Probably if you look across the US and China, it's definitely billions.
Yeah, that China is gearing up too. It's obvious that it's going to have a huge impact there too.
Yeah. Another question?
So I worry about applying machine learning in high-risk applications and try to quantify all of the sources of statistical uncertainty in the answers we give. And so the question is, how do I get my hands on how much uncertainty is being introduced by these various hardware hacks that are each maybe invisible to my software layer?
Yeah, that's a very good question, and I'm probably not the right person to answer it. I mean, I think if you are working with algorithms that are non-convex, then there are no real guarantees that I know of. Maybe someone who knows more can answer, but that's...
Well, so often we might want to train using all of the tricks that you're giving, but then take a validation set and run it through somehow very cleanly without the cache relaxations and all of those things. Mm-hmm. So we might want to have two modes for operating the hardware.
Yeah, I mean, that's perfectly possible, and you want hardware that can support that. Yeah.
Can these innovations serve a niche market of model training and inference, or is the expectation that overall training and inference workloads grow to some substantial portion of overall compute workloads in order to make this innovation vital and give it momentum?
Can you?
Is this a niche market for accelerators, or does it at some point take over?
So, in fact, the original, the original approach was to come up with a general purpose accelerator, right? So, as I said, it's not just machine learning, it's data analytics broadly, so it's SQL, it's graph. Anything that's data intensive could be accelerated using this approach.
Thank you.
Yeah.
I'd like to connect a couple dots, following up Tom's question of a moment ago at the same mic here. Hardware efficiency or computational efficiency feeds back to become statistical efficiency when your algorithms require a lot of hyperparameter search, other configuration search, and tuning in that sense. So the greater the computational efficiency, you may be increasing your statistical efficiency. So even the notion of kind of what the trade-off is here, I think requires a bit of nuance.
Yeah.
To be responsive to the fact that overall the machine learning problem includes the meta level of the learning. So I was just wondering if you've considered that or have any comments about that. Because I think that makes your story even stronger. I think that makes your story even stronger. So.
Yeah, I would agree, but I'm sorry. I would agree that there is this meta issue that you need to, however, I haven't given it a huge amount of thought. But yeah.
Okay.
Yeah. But we can take it offline.
All right. Thanks.
You want the details. Yeah.
Sure.
Hi. So I think one of the key components of software development is testing, and I think when it comes to machine learning, as opposed to standard testing mechanisms, it is quite hard because machine learning is stochastic by nature. And if you think about things like continuous integration, it's even harder because the data set that's being flown into the algorithms will change quite dynamically. So I was curious to hear your opinions about testing for ML in general.
Yeah, I think you're gonna have to do the same sorts of things that you do today with machine learning algorithms. I think don't fundamentally make it any better by having. I mean, you can. With greater performance, potentially you can look at more cases, but I don't see fundamentally what to do there. I mean, yeah.
Hi. I'm curious about the choice of a Scala programming language.
Yeah.
Is there any particular characteristic about Scala? Is that
well, so Scala is an artifact of some of the research that we did earlier, right? And so the reason to use Scala is it had a very expressive type system, and it allowed this technique called lightweight modular staging, which allowed you to basically virtualize the program that you wrote so you could get the whole IR, including control flow, into the representation, right? So you could apply this approach of staging where you could essentially put the compiler inside of the library, and it made it easy to do. And so that's why we use Scala.
Do you think
today, of course, in the machine learning space, the front end has to be Python.
Yeah, that's my question, actually.
But what you do in the back end, you could use whatever language you like, right? As long as you didn't expose it to the programmers.
Okay, thanks.
Yeah.
All right, we're out of time, but I'm sure Kunle will be happy to take questions offline. So let's thank Kunle again.
Thank you so much. Thank you. Is that understandable?